So the topic for today is integration. And so the first thing we have to learn is something called the Riemann sum. So you may or may not know that an integral represents the area under a curve. And one way that we can find the area under a curve between, let's say, this point and this point is to draw a bunch of little rectangles. I'm trying to see if I have a different color marker here. Here we go. So if I wanted the area under this curve, then I could compute the area of a bunch of rectangles. So I could draw a rectangle here, and then another one. Now this one is called the Riemann sum using the left endpoint. And the reason for that is because the left side of my rectangle is touching the curve each time. And they should be approximately the same thickness. So forgive my drawing. So each one of those, and we would add up the area of all of those rectangles. So each rectangle has a thickness that we'll call delta x. And if we wanted to find that thickness, our interval is b, or a to b, so delta x would be the difference between these two divided by the number of rectangles to get the thickness of each rectangle. So we call that n. So we need that guy, and we also are going to need the Riemann sum itself. So each one of these rectangles has a height and a thickness. The height of the rectangle is equal to the function at that point. Now, we can call that sub n, I guess, since we have n rectangles. So that would be f(x) sub n. So how do we find the area of a single rectangle? Well, the area of a single rectangle is f, let's say this is x1, x2, x3, and so on. So f of x1 is the height of the first one times the thickness delta x, plus the height of the second one times the thickness delta x, and so on. Well, this is nothing more than a sum of a bunch of terms. So we can write this as a summation. Instead of f of x, we can write f of x sub n. This delta x, we could make different. We could make it sub n. But in this case, we're going to say they're all the same thickness, so just all times delta x. And then this needs to run from n equal 1. Now, if we want to get the best possible option, actually we should make this, instead of n's, let's make this I. And I can make it run to n, right? N being the total number of rectangles. So subscript I, start at 1, run to n. Now if I want the area to be really accurate, then I need to take the limit of this as n gets really big, right? Because I want infinite amount of rectangles. So I'm going to take the limit as n approaches infinity. This is called the Riemann sum. Make sure I spelled his name right there. Nope, IE. And 2 N's. So Riemann sum. And what we're going to come to find out is that this can translate to what we're going to call the integral, the definite integral, which would be the integral from a to b, the interval that we were running over, of some function f of x, which is the curve, with respect to x. And there's also a little note there on your packet that talks about the fn int function. I'll do that in a minute when we do the example. So let's go ahead and try the first example here. And this might look daunting, but we only really have to do it a couple times before we can start learning how to integrate. So that's our function. We'll come back to that. All right, so the problem says graph the area represented. So our function is square root of x, and it is over 0 to 4. So the square root of x from 0 to 4 is going to look something like that. Okay, so that area under that curve, and it says create the definite integral to represent the area. So this is the graph, create the integral. So this would be an integral from 0 to 4. You plug the function in, and dx. That dx is our way of writing delta x in calculus. Okay. Use the midpoint rule with n equal 8 rectangles to approximate the sum. So the first graph that I showed you was using the left endpoint. We want to use the midpoint. So we have to find all of the endpoints first. So what are these endpoints? Well, they start at 0 and they end at 4. Well then, what is all the numbers in between? Well, recall we have this delta x, which is the interval 4 minus 0 all over the total number of rectangles, which in this case is 8. So that would be 1/2. So the endpoints are going to go up by 1/2 each time. So 0, 1/2. Go up another half, that's 1. Then 3/2, 2, 5/2, 3, 7/2, 4. Looks like we've lost some focus here. Here we go. What you see here? How do you know the rectangles will be 8? The problem says let n equal 8. That'll pretty much always be given to you. So these are our endpoints. And so now I need to find the midpoints. Well, the midpoints would be halfway between any of these two endpoints. So halfway between 0 and a half is 1/4. And instead of calculating it each time, this has to go up by a half, just like the endpoints do. Right? If the endpoints are 1/2 apart, so must the midpoints. And 1/2 is the same thing as 2/4. So 1/4, 3/4, 5/4, 7, 9, 11. Is that all of them? 1, 2, 3, 4, 5, 6. No, not quite. 13. So let's see, what 16/4 would be 4, so 15/4. So 1, 2, 3, 4, 5, 6, 7, 8. If there were 8 rectangles, there should be 8 midpoints. So that's good. And those are the values that you're going to be plugging into the sum. So remember, the sum was, we had limit as n approaches infinity. In our case, it's just 8. So we're just going to be doing the partial sum from I equal 1 to 8, f of x sub I, delta x. And I've always said that if delta x is the same for all of them, then you can bring it out of the sum. So Riemann sum for this one is delta x, which is 1/2, times the function evaluated at all of these these midpoints. So I need the function evaluated at 1/4, at 3/4, and so on. Okay, so all the way out to 15/4. So that's really going to be 1/2 times the square root of 1/4 plus the square root of 3/4, square root of 5/4, and so on. So go ahead and try and calculate that while I'm doing it. Okay, so I got 5.3522. So check me on that. And I will be right back, guys. The next thing that we need to do is to check to see how accurate our answer is. So we need to use the FNINT function. So to do that, we need to use our calculator. So if you have your calculator ready, you're going to go to Math, then scroll down. It is option 9 on many calculators, and you'll see FNINT. Select that. If you have an 84 plus, it should pop up automatically as an integral. So let's see if I can get this up here for you. So you should automatically get the integral symbol with the two positions that you can put in the values, and then the function, and then with respect to what variable. Sorry. So I've already calculated it once, but that's what yours should look like. If it does not, let me know. So I'll give you a minute to answer that. Alright, so I don't see anything yet, so I'm assuming you guys all have that function. So if you plug that in, right, you plug in your bounds 0 to 4, just like part B up here, then you should get, for the FNINT, it was 5.3, I believe, repeating. Let me check that again. Not quite. Bunch of 3s and a 544 at the end. But at least to the decimal places I have over there, it's all 3s. So not that bad. Right, and we just use little rectangles to get the area there. So that's pretty good, considering the shape. So there's another example, and it says to do this for sine of x. So same process. My function is now sine of x. My interval is 0 to pi over 2. My function then is going to look like this, right? Because this would be sine pi would be here, 3 pi over 2, and then 2 pi. So to its peak would be pi over 2. So the function looks very similar, which means we can probably expect the answer to be pretty close as well. We're going to go from 0 to pi over 2, and my function is now sine of x. Delta x, same number of rectangles, but this time we're doing pi over 2 minus 0 over 8. So that's what, pi over 16. So now my endpoints and midpoints need to change. Still starting at 0 and going up by pi over 16. So this would be pi over 16, 2 pi over 16, or pi over 8, 3 pi. Actually, I'm just going to leave it as 2 pi over 16 for now. 3 pi over 16, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. So there's two ways you can know you're there. That reduces to pi over 2. Or if there were 8 rectangles, then I need a total of 9 endpoints. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now to find the midpoints, which is going to be our most accurate, right, that has to be between two of these endpoints. So what is half of pi over 16? Well, that's pi over 32. And then again, I need to go up by a 16th. Pi over 16 is 2 pi over 32. So pi over 32 plus 2 pi over 32 is going to be 3 pi over 32, and so on. So just add 2 pi basically to the top each time, up until you have 8 terms. So 1, 2, 3, 4, 5. And again, this should make sense, right? I can't be any bigger than pi over 2 or 16 pi over 32, right? So that's where I stop with my midpoints. And again, there are 8 of them. So then if I want to do my sum, again, same thing, but now my delta x is different and my values that I plug in are a little different. Delta x is pi over 16, and the values I plug into my function are pi over 32, 3 pi over 32, all the way up to 15 pi over 32. And then down here, instead of taking the square roots in my sum, I am now taking the sine. So this is sine pi over 32 and sine 3 pi over 32 plus all the way to the end of 15 pi over 32. And then again, we also need to change delta x out here, which is pi over 16. So again, calculate that. Make sure that you're getting the same numbers that I am. If you're having trouble locating pi, it's above the caret on your calculator. And please, please, please remember to put your calculator in radian mode before you hit enter. This takes quite a bit of time to plug in. Alright, so just for the interior of the brackets there, I got 5.1. But then I need to multiply by pi and divide by 16. I get about 1, right? 1.0016. So this is 1.0 like that. And then we have to check the integral by doing the fnint function. So we can do that by going to, again, to math. Should be option 9. Should pop up just like that integral up there. Plug it in exactly how you see it. And for fnint, I get 1. So I always thought that was a a nifty one to remember. So let me ask you this. Knowing nothing about integration, I give you the sine, the integral of sine from 0 to pi. Can you tell me what that answer is? Good, that would be 2. Now here's an even better question. Again, not knowing anything about integration, what do you think the answer would be if I integrated from 0 to 2 pi? And don't plug it into the fnint function. I want you to think about it. So recall that the sine would look like that. All right. So if you did that, you would get 0. And the reason for that is you get 2 up here, but area above the axis is considered positive, and below the axis is considered negative. It's going to be just a second. I need to find my phone so that I can see your responses here. Can you guys all see the sheet, the worksheet? Of course, the chat's not appearing here, darn it. All right, for my view, I can see it there. I don't know why it gives you that big gap, but all right. So this here is the chart that you'll need to memorize. And first, before we talk about the chart, we have to talk about the fundamental theorem of calculus. So at the top of the page here, you see it says fundamental theorem of calculus. The fundamental theorem says that if you have a definite integral, which means one that has bounds, then the integral equals what we will call the antiderivative of the function little f. The antiderivative is represented here by big F. And notice we plug in the upper bound b, and we always subtract plugging in the lower bound a. One of the biggest things I always see with students is they don't like to do the minus the function at a. I don't know why. But you have to be very careful with that negative sign. So if the function is a combination of a bunch of terms, you have to distribute that negative to all of them. So here's a list of functions in the first and third columns here, and their antiderivatives. Now here's something that's nice. If you remember your derivatives really well, you've basically already got this memorized. They are called antiderivative for a very specific reason. So let me demonstrate. Let's look at the third one down, or fourth one down, in the second column. See, it says antiderivative big F is equal to tangent. What's the derivative of tangent? Well, you should remember that it's secant squared. Notice that that's the function little f here. So basically what that says is if I integrate secant squared, I get back tangent. So it is exactly the opposite operation. So the second part of the fundamental theorem of calculus is going to tell us later on that if we integrate a derivative, we're basically doing nothing. So let's just go through these. So integral of a constant. So if you just had a number, you're going to get back x. So just so you know what that would look like. And let's hope that this works here. I'm about to try to draw on the screen, and I hope that you can see it. Let's see if I scroll back here on my phone, if I can see it. So if I had the integral of just dx, for instance, that would equal x. Oh, it does work. Nice. And I can see how far behind I am now as well. So this guy right here is called a differential. And the integral of a differential returns the variable. So the integral of dy, for instance, is y. And I like to teach this to all of my calculus classes because my teacher did it for me. The integral of that. What do you think that equals? So answer in the chat. Correct. No question mark required. So if I have the integral of a differential, you just get back the variable. So that's where this first one comes from here. It says if you integrated a constant, right, so that's basically the integral of a constant times dx. Just like with differentiation, that constant can come out in front. Okay. Then we've got the integral of the sine. That is minus cosine. So that negative, remember that when we take the derivative of cosine, we get a minus sine. So in this case, we write it with the cosine. And again, that trick, right, any of the functions that start with a c have a negative in front of them. So if you integrate sine and you get back cosine, well, then you better put a minus sign in front of it. If you integrate cosecant squared, you get back minus the cotan, right? So any of them that come out with a c in the answer has a negative. Some of the ones that might, or the most interesting one, I guess, is probably the first one here on the second set, right? So column 3. So if we have an x to the n, right? So with the power rule for derivatives, we would subtract, or we'd bring the n down and then subtract 1 from that n. For integration, we're going to first add 1 to the n and then divide by that combination of n plus 1. So it's a little different, but still pretty close. Right? We're going to add 1 to the power, then divide by that number. You can still split them up if there's two functions added or subtracted. The 1 over x integrates to natural log, because remember the derivative of natural log is 1 over. The only difference here being that when you integrate, you do get an absolute value here, and that is important. Right, I might be a little lackluster in writing it sometimes, but it's very important in terms of plugging in the bounds that's given. Other than that, there's really no surprises here. All these are just directly from your derivative table, just written in reverse. So let's go ahead and try some of them. Let me ask you this real quick, guys. Would you prefer if I just write directly on this sheet the way I'm doing now, or do you want me to go back to the board? Anybody else want to weigh in? Alright, so I'll work on the sheet for a little while. See how that goes. Sometimes the pen does start to decide it doesn't want to write any longer, so we'll go until it craps out, I guess. Alright, so evaluate each definite integral using the fundamental theorem of calculus. So this first one here is just a constant, so I would pull the constant out in front. And I always tell people that I do these first few in excruciating detail, and then we can kind of move a little faster. So the integral of dx is x. and then I plug in the upper bound minus the lower bound. Now that's just because the function was x. If it was x squared, then this would be 7 squared minus 3 squared, and so on, which we'll see in just a second. So that looks like 20. All right, part B. This is the integral of x squared. So if I scroll back up here just a little bit, we can see that we need this rule. And it says add 1 to the power and divide by that number. So it's x squared. So it's x2 plus 1 over 2 plus 1. And so this is one notation here, or you can do the bracket 3, 7, or you can also do a line, which is another notation that this needs to be evaluated from 0 to 1. So this would be x cubed over 3 from 0 to 1. And then you go ahead and plug in. So this would be 1 cubed over 3 minus 0 cubed over 3. And please feel free to ask questions or stop me at any time. Right, I've done these problems millions of times, so it's like second nature for me. So if you have a question, please let me know. All right, this next one has 3 separate functions. All right, 2x squared plus 4x plus 1. So I'm going to break it into 3 different integrals. It'll be the integral from 1 to 3 of 2x squared. Now every time I break it up, I need a dx. And notice that this thing had parentheses around it that lets you know that that dx is distributed. All right. Now each one of those functions I can pull out the coefficient or the constant in front, constant multiplier. All right. So the integral of x squared is x cubed over 3. Right, we add 1 to the power and divide by that number. And instead of, actually, yeah, I'll go ahead and do each one separately and I'll put them all back together, I guess. Integral of x. So again, add 1 to the power. It's already the first power. So adding 1 becomes x squared all over 2. And then the integral of dx is just x. So now I'm going to put them all back together. So this is 2/3 x cubed plus, now 4 over 2, it's going to reduce to 2 x squared plus x, all evaluated from 1 to 3. So I did that just to demonstrate that you don't have to, after a while, you don't have to break it up as 3 separate functions. You can integrate it all at once. So then I plug in. So this would be 2/3 times 3 cubed plus, plug in 3 into this next piece. So that'd be 2 times 3 squared plus 3. Now it's important that we do minus and plug in the lower bound. But I'm going to put a set of parentheses here because I want to make sure that I get minus the entire thing. So 2/3, and now I plug 1 in everywhere. So let's see, we've got 2/3 times 3 cubed. That's going to be 18. So is this next term. Then we need to subtract everything that comes out of this second set. So this will be minus 2/3, minus 2, minus 1. So it looks to me like we can get rid of this and these two. And then we've got 36 minus 2/3. Or it looks like 106/3. So let's check that. Let's go to your fn function. And let's do the integral from 1 to 3. And plug in the function. So it was 2x squared plus 4x plus 1, all with respect to x. And I get 106/3. So it looks good. I don't know how to move the screen over. Let me go ahead and oh, here we go with the pen. There we go. All right. So any questions about that one, guys? Okay. So integral of sine. So remember, in order to get back sine as a derivative, we would need the original function to be minus the cosine. So when we integrate sine, we get minus the cosine. And this is evaluated from 0 to pi over 2. So this would be minus the cosine pi over 2 minus, always minus, a negative cosine of 0. So cosine of pi over 2, 0. Cosine of 0 is 1. This all comes out as 1. And in fact, we did that one earlier, right? That was one we did by the Riemann sum. So I've got, looks like 6 more examples here. So let's go ahead and do these. Please stop me if you're confused at any point. This next one is the integral of secant squared. So again, the derivative of tangent is secant squared. Therefore, the integral of secant squared is tangent. And then we just plug in the upper bound minus plugging in the lower bound. So that would be 1 minus 0 or 1. Alright, this next one here is a combination of two functions. We can integrate each one of them separately and then plug in the bounds. The integral of e to the x is our favorite because it's just e to the x. And the integral of x squared is, of x is x squared over 2. Right, add 1 to the power, divide by the number. Then all the heavy lifting is done, and we just have to plug in. So this would be e to the log 3 plus log 3 squared over 2 minus plugging in 0. Zero squared is still going to be 0. E to the 0 is going to be 1. And e and log cancel. So you have 3 plus natural log of 3 squared over 2 minus 1, or 2 plus natural log of 3 squared over 2. And no, you may not bring that 2 down and cancel it. So I'll just give that a second, and then we can go ahead and move on to the next few. Okay. So these next two are different because they have radicals. But remember that just like differentiation, we rewrote the radicals as powers. So I can rewrite this first one here as the integral of x to the 1/2 dx. And I follow the power rule. So I add 1 to the power, and divide by that number. So this is 1/2 plus 1 is going to give me 3/2, divided by 3/2. Instead of dividing by 3/2, I can multiply by 2/3. Actually, let's do this. 2/3 is going to get multiplied by everything, so let's just leave it outside. Of course, this is going to be 0 anyway. So four to the 3/2, so 4 square root is going to give us 2. 2 cubed is going to give us 8. So it is 16/3. Right, H is very similar. We need to rewrite it. Because it was in the denominator, right, I need to make it negative power. And it's just a third root, so minus 1/3. Again, I add 1. So negative 1/3 plus 1 is 2/3. Divide by that number, which means I'm now multiplying by 3/2. And from 1 to 8. So plug 8 in there. 8 to the 2/3 minus 1 to the 2/3. So cubed root of 8 is 2. 2 squared is 4. 1 to any power is 1. So it looks like 9/2. So again, I'll leave that there for a minute or two. Okay. Make some room here. So the next problem, we've got square root of 1 minus t squared. So let's scroll back up here. That looks an awful lot like this guy. Except x is now t. So it says if I integrate that function, I get back arc sine. So this is just 2 times, so that 2 can go out there, which means I get 2 times the arc sine of t, and this is evaluated from 1/2 to square root of 2 over 2. So plug in square root of 2 over 2, and then second plug in 1/2, remembering to subtract it. So the first one is pi over 4. And the second one is pi over 6. And you can get those from your unit circle. So that comes out as pi over 6. But again, plugging in part isn't hard, it's the integration because it's new. That last one looks an awful lot like the arctan. So 1 over x squared plus 1. So this is 3 over x squared plus 1. Again, that 3 could be thrown out in front. So that's 3 times the arc tan of 1 minus the arc tan of root 3 over 3. All right, so arc tan of 1 is pi over 4. And the arctan of square root of 3 over 3 looks like it is also pi over 6. So this time we get 3 times pi over 24. So we've got 2 pi over 8 or pi over 4. Please scroll down a bit. Can you see it okay or no? No, you can't. There you go. Sorry, I can only see what you were seeing or see the chat. I can't see both at the same time on my phone. So, any questions about those problems, guys? It's 2 pi over 24. There you go. Alright, so I just have, I believe, these last 4 here to do. So I'm actually going to do these on the board, I think, because I want to be able to show you the pictures. Alright, so is everybody okay with those? Just real quick, I want to check the syllabus. See how we're doing here. I think we're on track, but I just want to check. So yeah, according to this, we were on, we had the exam a day early from the original setup. Okay, we're rolling along. Alright, so like I said, let me do these last couple problems. And then if there's any time left, you're welcome to ask any questions you have, or if you want to ask me something about the test or something like that, then that's fine as well. Alright, so we've talked about the idea that the integral represents the area under the curve. And so sometimes there are cases where it might be easy to go ahead and solve the integral by finding the area of the shape. So this one's kind of silly. It's just 7 dx. Not sure why the focus is off again. Give me just a second. A little better, I guess. Okay, so 7 dx, and so what does that look like? Well, that's the line y equals 7, and if it's from 1 to 3, well, something like this region. So we could very easily integrate this, right? This would be 7 integral dx, and that would be integral of dx is x from 1 to 3, so that's going to be 7 times 2, or 14. Well, how else might we do that? So as I said, we could do it by the shape, right? If this is 1 to 3, well then this distance has to be 2, and the height has to be the height of the function, which is 7. And we know that the area of that little rectangle is, yet again, 2 times 7. Okay? So we can do it both ways and get it very easily. Here's another one. Integral of x plus 2 dx, and this is from 2 to 5. So again, what does the line x plus 2 look like? Well, it passes through 2, and it has to have a positive slope of 1, right? So it looks like something like that. And they're saying from 2 to 5, so from here to here, so that is some kind of rhombus, right? But I can actually cut this off and create a rectangle and a triangle. Again, not hard to do by just the integration, but it's good to know to be able to do it with the graph as well. So what's this rectangle? Well, at x equal 2, if the function is x plus 2, right, y has to equal 4 here. Right, because x is 2, then you get 4. And when x is 5, what's this value up here? Well, that's 7. So the height of this rectangle is 4, and the thickness is 3. right, because it's 5 minus 2. So for the rectangle, the area is 4 times 3, or 12. And we just need then the triangle. So remember, the area of a triangle is 1/2 its base, which is 3, times its height. Well, if this is 4 and that's 7, then its height is also 3. So you get 9/2, and so the total area is 12 plus 9/2. So 33/2. Just check myself on my mental math there. That's good. Okay. So those two are really easy to do by integration. The next two are not. And are there any questions about these before I do the next two? All right, so I'm not seeing anything, so I'm going to continue. So this next one says the absolute value So nowhere in that little chart that I gave you at the beginning did you see absolute value. Come on, camera. All right. So what does the absolute value of x minus 5 look like? Well, we know that absolute value looks like this. So what does the absolute value of x minus 5 look like? Is it shifted left or is it shifted right? So I'm asking you guys. Is it shifted this way or shifted that way? So you might think that, but it's actually shifted this way. So that's 5. So we can create from 0 to 7. So they want the area here and they want the area out at 7, so also that area. So it's two triangles that we can do. This triangle has a base of 5. This triangle has a base of 2, because this point is 5 and this is 7. Now the question is, what's the height? So when you plug 0 into the absolute value here, you get back 5. And for this one, you plug in 7, and you get back 2. So the total area is the area of this triangle, which is 1/2 its base times its height, plus 1/2 the triangle for this, which is base height. So 25 halves plus 4 halves is 29 halves. And as of right now, right, we haven't discussed how to integrate the absolute value. So you currently do not have an idea of how to do that. So the graphing was actually good for that case. And then let me go ahead and finish up here with the last one, which is the square root (4 - x squared) from 0 to 2. So again, the question is, what does that look like? So if we plot that, you might recognize that as a part of a circle. That is the top half of a circle with a radius of, should be 2. So that distance is 2. And it says to go from x equals 0 to x equal 2. Well, this is x is 0, this is x equal 2. So we don't want this piece at all. We just want this area. And you might be thinking, well, I have no idea what to do with that. But we just got done saying this is a part of a circle. It's in fact 1/4 of the area of a circle. So 1/4, the area of the circle is pi times r, which in this case is 2 squared. 2 squared is 4. We're dividing by 4. Pi. Again, you will have no idea how to do this integral until you take Calculus 2. So that's a pretty powerful tool to be able to find that.